This conference will now be recorded.
Good morning, students. In today's class, we are going to discuss about torque equation of three-phase induction motor. So till now we discussed the rotor parameters which was affected by the slip. So in fourth unit, you have four important questions you may get in a semester exam. One is construction of three-phase induction motor. Second one is the effect of slip on rotor parameters. Third one is torque equation, and fourth one is torque slip characteristics. So these are the four important questions you will get from fourth unit. So based on the construction, how many types of three-phase induction motor? So in construction point of view, how many types of three-phase induction motor? Students, can you hear my voice? Right. Today we are going to discuss about torque equation of three-phase induction motor. So let's move on to the topic. So how we are comparing the three-phase induction motor for which device? Which device we can compare with the three-phase induction motor? Right. So if you take that, so the three-phase induction motor is compared with transformer, right? So here we are talking about the working operation of transformer with respect to the power. So what is the power formula for transformer? What is the formula for power in transformer? Right. P is equals to VI cos phi. Right. Now here the three-phase induction motor is comparing with the transformer in the point of working principle. So the only difference with respect to transformer and three-phase induction motor is rotor. So in three-phase induction motor is we have stator and rotor. In transformer is we have primary and secondary. So here the secondary is compared with rotor. Now if you want to talk about power, it is related to the secondary of the transformer. because the secondary is connected to the load, right? Similarly, in three-phase induction motor, the rotor is connected to the load. So that's why in the point of three-phase induction motor, we are talking about torque. At the same time, in the form in the point of transformer, we are talking about power. Now, here we are going to be derive that what is the torque equation of a three-phase induction motor. Generally, in three-phase induction motor, we are going to talk about two cases. One is starting condition, another one is running condition. Now we are going to derive the torque equation with respect to these two cases. So what is the torque equation at starting condition and what is the torque equation at running condition? Now let me see that how we can derive this equation. Right. So here the torque is developed on the rotor, right? So we are talking about secondary of the three-phase induction motor, that is rotor. Now the torque is T developed by the rotor is directly proportional to that. One is rotor current, rotor EMF, and power factor. So similarly, what we seen in the power of a transformer, that is P is equal to VI cos pi. In that, the power is depends on that voltage, current, and power factor. Similarly, the torque of three-phase induction motor is related to that. It is depends on the induced EMF on the rotor, that is denoted by E2. Rotor current, it is denoted by I2, and power factor, so cos pi 2. This is the parameters which are involving to the torque development, right? The torque development should be based on that induced EMF on the rotor, rotor current, and cos power factor. Now here we can represent this relation. T is directly proportional to E2 I2 cos pi 2. Now if you want to eliminate this proportionality, we have to add one proportional constant. T is equal to K into E2 I2 cos pi 2. Now I2, the rotor current at standstill, E2, rotor EMF at standstill, cos pi 2, rotor power factor at standstill. So standstill means at starting condition. So what is the value of S at starting condition? What is the value of S at starting condition? Right one. So now if you want to represent these parameters at running condition, how we can write? I2 is equals to I2R equals to SI2. E2R is equals to SC2. So these two equations we can represent in running condition, because running condition S should be vary between 0 and 1. So remember one thing. So here the torque we are going to be derived in two cases. One is at starting condition, second one is at running condition. At starting condition we are going to be represent S is equals to 1. At running condition we are going to consider S. Okay now the values of rotor EMF, rotor current, and rotor power factor are at the given at the starting condition. Okay so we are going to be derive this torque equation at both cases. So this is the initial formula for torque. T is equals to K into E2 I2 cos pi 2. Now if you want to represent this, if you want to simplify this equation, you have to know that what is the formula for E2 and what is the formula for cos pi 2. So already we've seen these formulas in rotor parameters affected by the slip. So I2 is equals to, we can write V by R, that is E2 divided by Z2. Now we can write this one, E2 is equals to E2 divided by square root of R2 square plus X2 square. Now how we can write the cos pi value? R2 divided by R2 square plus X2 square. Now in these two equations, if you see that these two equations, which parameter was influenced by the slip? So when compared to this two equation, which parameters are influenced by the slip? సో ఇక ఈ టూ ఈక్వేషన్ లో ఏ పారామీటర్ కి స్లిప్ ఇన్వాల్వ్ అవుతుంది? Right. So not cos phi. Also here we can represent this the influential parameter which was affected by the slip is rotor induced EMF E2 and X2. Suppose if it is starting condition, you can write this equation. If it is running condition, you have to represent SC2 SX2. So this is a running condition. So remember these two equations, and these two equations are using in the simplification of torque equation. Right. Now we are going to derive the torque equation at starting condition. So remember one thing, at starting condition S is equals to always 1. In this condition, the rotor is not rotating. So we can simply say that rotor is a standstill condition. Now here these three parameters are involving for the torque. One is rotor induced EMF, rotor reactance, rotor resistance. Now here we know the value of the torque equation, right? T is equals to K into E2 I2 cos pi 2. So this is the torque equation. Now I am going to represent here TS, that is starting torque, is equals to K into E2 into. So here I can write I2 in the by the replacement of E2 by Z2. So E2 divided by square root of R2 square plus X2 square. So how we can get this value Z2 as a R2 square plus X2 square? From right angle triangle, right? So from the right angle triangle, you can write here R2 is there, here X2, and it is the Z2. So you can write Z2 is equals to square root of R2 square plus X2 square. So this is the equation we had to replace in the place of I2. Next, cos pi 2. So what's the formula for cos pi 2? Adjacent side divided by hypotenuse, R2 divided by Z2. So R2 divided by R2 square plus X2 square. Now these two parameters, that is I2 cos pi 2, we had to substitute in the torque equation. So TS is equals to K into E2 into, in the place of I2 I am going to substitute E2 divided by square root of R2 square plus X2 square into R2 divided by square root of R2 square plus X2 square. Now if you multiply these two equations, the denominator having the same factor which is in the square root. So you will get whole term by square, right? So square and root will be get cancelled. K into E2 square R2 divided by R2 square plus X2 square. This is the torque equation at starting condition. TS is equals to K into E2 square R2 divided by R2 square plus X2 square. Now how we can obtain the K value? So for three-phase induction motor, the K value we can write 3 divided by 2 pi ns. How we can obtain this constant value means here the 3 represents that what is the phase we are obtaining the power to the induction motor. So we are applying the 3-phase power, right? That's why here 3 was kept. Divided by 2 pi. One single rotation takes that 360 degrees. So that's why we can write reference 2 pi. And this is the rotor EMF which is rotating at the synchronous speed. So 3 divided by 2 pi ns. So from the replacement of k, you can write ts is equals to 3 divided by 2 pi ns e2 square r2 divided by R2 square plus X2 square. This is the equation of starting torque. Now, for this, we need to find that what is the maximum starting torque. అంటే maximum starting torque అనేది ఎటువంటి కండిషన్ లో అవైలబుల్ గా ఉంటుంది. So that we need to find that. So అది ఎలా అంటే ఇప్పుడు for example, if you take the transformer, right? So you will get one question. So what is the maximum condition for efficiency of a transformer? అంటే maximum efficiency ని అప్టైన్ చేయడానికి ఎటువంటి కండిషన్స్ లో ట్రాన్స్ఫార్మర్ అవైలబుల్ గా ఉంటుంది. So the maximum efficiency condition for transformer, that is when copper losses is equals to iron losses. This is the condition. ఎప్పుడైతే copper loss, iron losses రెండు ఈక్వల్ ఉంటాయో, then that transformer will give that maximum efficiency. Similarly, the three-phase induction motor are having some condition to obtain the maximum starting torque. Now we are going to be derive that what is the maximum condition, maximum torque condition for three-phase induction motor. Right. So here, let me see that the in this equation we are going to be eliminate that constant parameter. So we obtain the equation like this, right? Ts is equals to K into E2 square R2 divided by R2 square plus X2 square. Now here, in this equation, some parameters are constant and some parameters are variable. Let me see that what are the parameters are constant and what we have to do. Generally, the stator supply voltage V is constant. So we already open transformer lo supply voltage entaithe istamo with respect to the EMF also same, because from the transform ratio we can obtain V2 divided by V1 is equals to E2 divided by E1. So the voltage is directly proportional to the induced EMF. Similarly, in three-phase induction motor also, how much of voltage we are applying to the stator, the same EMF will be induced here. So the V is constant, so that flux per pole pi set up by stator is also fixed. This is terms means the EMF induced in the rotor will be constant. That's why we have to eliminate this equation, that term E2, because it is a constant value. And we can again rewrite that starting torque equation. Ts is equals to K1 R2 divided by R2 square plus X2 square. So here E2 is constant, right? So that's why I am eliminated this. So finally K1 R2 divided by Z2 square. So this is the starting torque equation when induced EMF as a considered as a constant. Now it is clear that the magnitude of starting torque would be depend upon relative values of R2 and X2. Now, if you see this equation alone, in this equation only we have R2 and X2, right? So that's why the completion of torque equation is depends on that rotor resistance and reactance and the standstill rotor. So here this is the equation. Now the replacement of proportional constant K we can write 3 divided by 2 pi ns. This is the final equation of a three-phase induction motor at starting condition. Okay. Now here the rotor speed, the speed ns is in RPS. So we had to represent in RPS, rotor per second. Now we will find that what is the maximum torque condition for three-phase induction motor. Right. So this is the equation condition for maximum starting torque. Okay. Now you guys are seeing that mathematical formulas and mathematical conditions in mathematics, right? That is a differentiation and integration. So what is the use of differentiation? So at what condition we are going to be use differentiation? ఎక్కడ యూజ్ చేస్తారు differentiation ని? So you guys are did in mathematics, right? So what is the use of differentiation? Right. Differentiation is a mathematical equation and mathematical condition which was used for obtaining the maximum value. Suppose if you having that one condition, so ఒక ఈక్వేషన్ ఉందనుకోండి, ఆ ఈక్వేషన్ అనేది ఏ పాయింట్ బేస్ చేసుకుని మాక్సిమం అప్టైన్ చేయగలుగుతాం. సో ఫర్ దట్ యూ నీడ్ టు అప్లై ద డిఫరెన్షియేషన్ ఫర్ దట్ ఈక్వేషన్. Similarly, I am going to be apply the differentiation for this equation starting term. So here E2 is constant. Okay. Now, if you eliminate this equation, parameter, you may get the equation Ts is equals to K1 R2 divided by R2 square plus H2 square. Now, for obtaining the maximum condition, we are going to be derive this torque equation with and equating to the 0. So, dTs divided by dR2 equals to 0. Why I am going to represent R2 అంటే R2 ఎందుకు తీసుకుంటాను అంటే మనం స్పీడ్ పెంచాలన్నా తగ్గియాలన్నా దేనిపైన డిపెండ్ అవుతుంది, రెసిస్టెన్స్ పైన డిపెండ్ అవుతుంది, ఎక్స్టర్నల్ రెసిస్టెన్స్. సో దట్స్ వై ద రెసిస్టెన్స్ ఇస్ ద పారామీటర్ విల్ డిసైడ్ దట్ టార్క్. దట్స్ వై ఐ am going to be differentiate this torque equation with respect to the R2. Now K1, how we can apply this equation? By using which formula? సో ఈ టర్మ్ అనేది ఎలా వచ్చింది? Do you know that u by v equation, differentiation of u by v? Right. So from this equation, we are going to obtain this equation, right? So let me take the K1 is a constant. First, R. So if you differentiating this R with respect to R, right? 1 divided by R2 square plus X2 square minus. See, this is the equation. What V into U dash minus U into V dash. So I will give the clarity in this. So the differentiation of U by V is V into U dash minus U into V dash divided by V square. Right? Now, first, what is the V here? R2 square plus X2 square into U dash. U dash means numerator. So you will get 1 minus U into V dash. So U is R2 into V dash means the denominator R2 square plus X2 square. So X2 is constant, it will become 0, and R2 square you will get 2R2. 2R2 divided by R2 square plus X2 square whole square. If you take that first term, 1 square will get cancelled, then you will get 1 divided by R2 square plus X2 square minus 2R2 square divided by R2 square plus X2 square whole square equals to 0. Now from this relation, how we can, what you are going to be obtained means, see, if you consider this equation, just cross multiply this to this equation, right? So 1 divided by R2 square plus X2 square minus 2R2 square divided by R2 square plus X2 square whole square equals to 0. If you simplify this equation, what you will get? 1 divided by R2 square plus x2 square equals to 2r2 square divided by r2 square plus x2 square whole square. Here 1 get cancelled. If you cross multiply this, you will get r2 square plus x2 square equals to 2r2 square. Now this is the condition for obtaining the maximum torque. Now when this equation satisfies, when r2 equals to x2, so when r2 equals to x2, then it will satisfy this condition. Okay now, so make example adagachu. What is the maximum, what is the condition for maximum starting torque? The condition is when r2 is equals to x2, then you will get that maximum starting torque. Okay now, so that is rotor resistance per phase is equals to standstill rotor resistance reactance per phase. So this is the condition for maximum starting torque. Are you clear? అర్థమైందండి ఇది? I clear this derivation, otherwise you need again. Right. So we are going to now we are going to derive the torque equation for second case, that is at running condition. Right. See here, this is the relation for maximum condition. Under the condition of maximum starting torque, the pi 2 is 45 degrees and rotor power factor is 0.707 lagging. Now you can obtain, you can see from here. Now the figure shows variation of starting torque with the rotor resistance as per the rotor resistance is increased from a relatively low value. Now if you see this, this is the starting condition. At starting, this is the maximum point. At this point, so just observe here, this is the point we are getting the maximum starting torque. Now from this you can see that when the rotor resistance is keep on going to be increased, the starting torque also increases. So both are vice versa. That's why this is the condition we can obtain that R2 is equals to X2. So here the slip is equals to 1 at this condition because it is a starting condition, right? Now we are going to be derive the torque equation for running condition. Right. Effect of change of supply voltage. Right. Suppose in previously we are going to be assumed E2 is a constant, right? Suppose if the supply voltage will be changed, what will happen? That the supply voltage will be changed. It is completely change of the torque equation because the torque is directly proportional to that induced EMF E2 square. If supply voltage is changed, EMF also change, automatically torque also change. So this is the effect of change of supply voltage. ఇక్కడ మీరు అబ్జర్వ్ చేస్తే 10% సప్లై వోల్టేజ్ చేంజ్ అయితే 20% టార్క్ ఇంక్రీజ్ అవుతుంది. ఓకేనా? సో బికాస్ ద టార్క్ ఈస్ స్క్వేర్ టర్మ్స్ ఆఫ్ ఇండ్యూస్డ్ ఈఎంఎఫ్. ఓకేనా? రైట్. So this is no need. Now let me see that the torque equation under running condition. Now let me take that the parameters which are influenced by the slip at running condition. you can write E2 dash. So you can write E2R also. E2 dash is equal to SE2, X2 dash is equal to SX2, and you can write that impedance R2 square plus XS2 square and current. So ఇక్కడ మీరు అబ్జర్వ్ చేస్తే E2 కి X2 కి S అనేది మల్టిప్లై అయింది బికాస్ ఆఫ్ at running condition S should be very lies between 0 to 1. So that's why I'm going to be substitute here. Now from the torque equation at running condition, TR is equals to K, that is proportional constant, E2R I2R cos pi 2R. Now we are going to be substitute this equation in these terms. So you will get TR is equals to, that is running torque equals to K E2R. Instead of I2R I can write E2R divided by square root of R2 square plus SX2 whole square. Similarly for cos pi also you can write R2 divided by R2R divided by square root of R2 square plus SX2 whole square. Now let me see that how we can apply the torque equation at running condition. So this is the equation that is starting torque, sorry, running torque proportional to so pi. So here pi is equal pi into SE2 into R2 divided by R2 square plus S2 square. So here 1 E2 is denoted as a pi 2. So ఇక్కడ నేను E2 okay E2 నేను pi గా ఇండ్యూస్ చేస్తాను because of the induced EMF should be depends on the flux, right? So how much of flux should be cut by the conductors, then EMF will be induced. So okay E2 బదులు నేను pi అని అజ్యూమ్ చేసుకున్నాను. So finally the running torque is directly proportional to pi SE2 R2 divided by R2 square plus SX2 square. Now from this equation we can write that torque equation. So when it is supply voltage is constant, E2 also constant. Okay, so finally the torque at running condition is equal to K2 into S R2 divided by R2 square plus SX2 whole square. So ఇక్కడ మనకు ఓన్లీ S అనేది ఇంట్రడ్యూస్ అయింది. Okay, now we are going to be derive that maximum condition. See here this is the full form of torque equation under running condition. So it can be seen that the value of K1 that is given by 3 divided by 2 pi ns. So here also we can substitute TR is equals to 3 divided by 2 pi ns S into E2 square R2 divided by R2 square plus SX2 whole square into 1. At starting condition you will get this equation. So this is the torque equation at starting condition. It is the torque equation at running condition. Remember these two equations, very important. Now we are going to be find that the maximum torque condition. Right. So this is the way we are going to be make that maximum torque under running condition. Okay. Now in order to find the value of rotor resistance, so if you see if you simplify this equation, you will get, so R2 is equals to SX2. So this is the maximum condition at running condition. At starting condition R2 is equals to X2. So this is the at starting condition. See, let me see that the simplification of this equation. So this is in the form of U by V rule. If you apply the differentiation to the U by V rule, you will get U into V dash minus V into U dash divided by V square, and it is equating to the 0. Next, finally, after simplification of this equation, you will get R2 square plus X2 square minus 2SX2 square. So from this, you will get finally This is the maximum torque under running condition. R2, the rotor resistance per phase is equals to frictional slip into standstill rotor reactance. Okay, now from this equation, you will get that what is the maximum torque at running condition and what is the maximum torque at starting condition. Now I will draw the equations again for simplification. First, the starting condition. At starting condition, that starting torque is equals to Ts is equals to 3 divided by 2 pi ns into E2 square R2 divided by R2 square plus X2 square. This is the starting torque equation, and the condition for maximum starting torque is R2 is equals to X2. Right now, let me write that running condition. The torque at running condition is equals to 3 divided by 2 pi ns into S E2 square R2 divided by R2 square plus Sx2 square. Now the condition for maximum torque at running condition is R2 is equals to Sx2. Yeah. So this is the way we are going to be derive the torque equation at two cases. One is starting and running torque. Now from this, for maximum torque we can obtain at R2 is equals to Sx2. So this is the equation. Now instead of Sx2, so ఇక్కడ Sx2 plus లో just R2 substitute, the T R is directly proposed to R2 divided by R2 square plus R2 square. So you will get 2 R2 square. R2 divided by 2 R2 square. 1 R2 get cancelled. Finally, you will get Tm is directly proportional to 1 divided by. So I am representing in terms of x2, 2x2. Okay, na? So this is the obtained condition. Now for the placement of S, if we substitute R2 by x2, R2 by x2 ni equal substitute emotion joined. If you substitute this equation in this here, then you will get that maximum torque. Now from this above equations, we are going to be observe these four parameters. What is the four means? The first one, the value of rotor resistance does not alter the value of the maximum torque, but only the value of slip. So we have the two parameters, right? R2 and X2. So in these two parameters, which parameter is changing based on the running condition, starting condition? ఏ parameter change అవుతుంది ఈ రెండిట్లో? At both cases. Which parameter was changing, R2 or X2? No, R2 is never changed. The only parameter X2. So if you see this, at starting condition R2 is equals to X2, right? At running condition R2 is equals to Sx2. So here reactance was influenced by the slip. Okay, na? X2 change avutundi. Okay, na? Right. Next, the maximum torque varies inversely as the standstill reactance. Okay, na? So Tm is inversely proportional to that reactance X2. Okay, na? So this is the condition we seen from the above equation. Next, the maximum torque varies directly with square of the applied voltage, because T is directly proportional to that E2 square, right? Here E2 is the rotor induced EMF and which is equals to the supply voltage. So T is, you can write T is directly proportional to the supply square of the supply voltage, and To obtain the maximum torque at starting and S is equals to 1, the rotor resistance must be equal to that rotor reactance. So this is the final one. We are getting that at starting condition for obtain the maximum torque, we the rotor resistance is equal to rotor reactance. At this condition, S is equals to 1. So this is about torque equation of three-phase induction motor. So we have only one topic remaining in this fourth unit, that is torque slip characteristics of a three-phase induction motor. In next class, we are going to be solve some problems based on the torque equation. After that, we are going to discuss the torque slip characteristics. So okay, students, this is about today's class. So I am going to end this class. Thank you.